If I can't picture it, I can't understand it. Albert Einstein. Dear students, welcome. Till so far we have discussed how to calculate work of a force, and we have deduced work-area theorem for an inertial frame and on a single body. And we have seen its application in such situation, that is in an inertial frame on a single object. Today we'll discuss the use of work-area theorem in some other inertial frame that is moving with some velocity, and especially in non-inertial frame. Thereafter, we extend our discussion on the use of work-area theorem on a system of particles. If you see a system of particle, what does it mean? It means a system consisting a finite number of particles, or a system consisting a finite number of bodies, and all these bodies must be in translation motion, and that was our interpretation of particle. In kinematics, we have defined that a particle is either a point mass or a body irrespective of size that is in translational motion. So let us proceed with our talk today in this lecture. Here, if you see on this screen a diagram in which a truck, and on the truck there is a box. Suppose this truck is moving with some velocity and we apply some forces on this box. If the truck is moving with a constant velocity, the reference frame of the truck is an inertial reference frame. And if we apply forces on it, how the box will move and what will be its velocity with respect to truck after some time? That is area today of discussion. And if the truck is moving with some acceleration, the reference frame attached with the truck will be a non-inertial frame. And if we apply forces on the box, what velocity the box will acquire after some displacement, that is area of application of non-inertial frame. And if you see in the second diagram, you see this object B and this bracket A and C, they are interconnected by string and pulleys, and that we call a system of particle. How we apply work-area theorem on this system of particle? One way, what we have seen earlier, we can apply work-area theorem on each body separately. Can we apply the work-area theorem on the entire system as a whole? And if we try to apply the work-area theorem on an entire system as a whole, what we have to do? We have to explore all these ideas today in this lecture. So let us proceed. First, we revise what was our work-area theorem. Work-area theorem states that work done by all the external forces acting on a particle in carrying it from one position to another is equal to the change in kinetic energy of the particle between these positions. And if you write mathematically, the statement is like that: W initial to final is equal to summation Ri to Rf F dot dr is equal to K final minus K initial. Here F dot dr, integrate from Ri to Rf, is work done by this force F. If you put here summation sign, it means it is this term will be equal to work done of all forces, and that is what we mean by W initial to final, and that will be equal to change in kinetic energy K final minus K initial. K final stands for final kinetic energy and K initial stands for initial kinetic energy. Work-area theorem and inertial frame. Now what we do in some other inertial frame, suppose for inertial frame this statement is true, but we choose some other inertial frame that is moving with a constant velocity. What we do in that frame? Of course, Newton's law is valid on that frame also, and we have deduced work-area theorem from Newton's second law, so work-area theorem must also be valid in that frame. And what care we to take? We have to calculate work done with respect to the frame under consideration, as well as we have to consider kinetic energy with respect to frame under consideration. And let us document this idea. This theorem is valid in all inertial frames. How it is made valid? To apply the theorem in any inertial frame, account for the work done by all the forces on the body as well as the change in kinetic energy of the body with respect to the frame under consideration. It means if you apply work-area theorem in some other inertial frame, what we to do? consider work of all the forces in that frame which we are considering, and initial and final kinetic energies in that frame. Similarly, we can extend our idea how to use work energy theorem in a non-inertial frame. Again, work energy theorem was deduced from Newton's second law. If you see, Newton's second law will become valid if we consider pseudo forces also. So by considering work done by pseudo forces, we can make the work energy theorem valid in a non-inertial frame. That is what work energy theorem is valid in a non-inertial frame if work done by pseudo force is also considered. And how we apply work energy theorem in a non-inertial frame, let us see. To apply the theorem in a non-inertial frame, work done by the pseudo force in addition to that of the physical forces and change in kinetic energy of the body with respect to the frame under consideration must be accounted for. It means, I will explain further, the work of pseudo force and work of all physical forces must be calculated with respect to the frame under consideration, as well as initial and final kinetic energy must also be calculated with respect to the frame under consideration. Now we will see how to use work energy theorem in an inertial frame or non-inertial frame is again not a complex idea. We'll try to understand these ideas in some more detail by considering some examples. Example 1, work energy theorem in an inertial frame. Let us see what the example is. A box of mass m is placed on the flatbed of a truck that is moving at a constant velocity u on a level road. The coefficient of friction between the box and the flatbed is mu. A constant force F is applied on the box in the direction of motion of the truck. Find speed of the box with respect to the truck after the box slides a distance x with respect to the truck. Now we'll see. Displacement x is given with respect to the truck and speed of the box is asked with respect to the truck. So it is natural to use the frame of truck, and it is given the truck is moving with a constant velocity u. So the truck is a inertial frame here. Now what we do, there are no pseudo forces. We have to calculate work of all the forces on the box with respect to truck and equate it, change in kinetic energy of the box with respect to truck. So the diagram of the problem is given here. You can see the truck and here is a box, and on the box a force F is applied. Now how we'll proceed? Let us see. Consider a frame attached with the truck. Initial velocity of the box relative to the truck is 0 and the final velocity, let us assume it is v, and we can see here. And finally the box has slid a distance x and force F is continued to apply, and here let us see its velocity becomes v. Now what we do, first we calculate initial and final kinetic energies of the box. Let us see initial and final kinetic energies. So K initial is certainly 0 because speed of the truck with speed of the box with the truck is 0, and final kinetic energy is half mv square because speed of the box with respect to truck is v, and that is what kinetic energy of the box with respect to truck, and this is kinetic energy initial of the box with respect to truck because the box was at rest initially with respect to truck before the force was applied. Now we calculate work done by all the forces, work done by various forces on the box. For this purpose, we'll draw the FBD of the box, means free body diagram, at some intermediate stage. Let us see here. The box is here and forces acting on it are the force applied F, its weight mg, the normal reaction that will be equal to mg, and frictional force that is kinetic, and that will be equal to mu mg. So let us see here. What is the work done by gravity? It will be 0 because the displacement x is perpendicular to mg. So work done by gravity is 0. Similarly, work done by normal reaction will be 0 because the displacement of the box is perpendicular to normal reaction. Now we calculate work done by the force F. So WF will be F into x because F is a constant force. Similarly, we can calculate work done by friction force. Friction force is also constant, but it is opposite to displacement, so this work will be negative. So W by friction will be minus mu mgx, and mu mg is the magnitude of friction force. So we have calculated work by all the forces. Now what is remaining? We'll substitute these values in the work energy theorem. Substituting these expressions in the work energy theorem, we get W initial to final is equal to K final minus K initial is work energy theorem. So instead of W initial to final, we use Wg plus Wn plus Wf plus W small f. Small f represent for friction. So Wg plus Wn plus W applied force plus W friction is equal to K final minus K initial. Let us substitute the values. That is 0 plus fx minus mu mgx is equal to half mv square minus 0. By solving this, we can get what is velocity of v. That is 2f minus mu mg x common upon m square root. Now, how we arrive on that result, you can verify it. You can see how simple was to apply the work energy theorem in an inertial frame. What we have done, we have decided earlier that whatever frame is, if it is inertial, to apply work energy theorem, calculate work done by all the physical forces with respect to the frame, and consider initial and final kinetic energies with respect to frame. On the same line, to apply work energy theorem in a non-inertial frame, what we do? We have to consider work done by the pseudo force in addition to all the real forces or physical forces with respect to the given non-inertial reference frame, as well as we have to consider initial and final kinetic energies of the box or the body with respect to the given non-inertial frame. Now, let us extend this idea how we can use the work energy theorem in a non-inertial frame in the next example. Example 2, work energy theorem in a non-inertial frame. A small box starts sliding down a frictionless inclined plane which is moving in a horizontal direction with a constant acceleration a0 as shown in the figure. Find the speed of the box with respect to the plane when it descends a height h. See here in this figure, the inclined plane is given. Inclination of the plane is theta, and this inclined plane is moving towards left with a constant acceleration a0 without rotation, means its inclination is a constant. Now how we'll do? As we have discussed, we'll consider work done by the real forces. That we can see the real forces are what? The gravity and the normal reaction, because there is no friction. And work done of the pseudo force, that is mass of the body and reverse acceleration of the reference frame multiplied. So ma0 is the pseudo force, and that will act towards the right. We have to consider work done by all the frames with respect to the inclined plane, that is our non-inertial frame, as well as we have to consider initial and final kinetic energies with respect to this non-inertial frame attached with the inclined plane. So we'll proceed with the same line as we have discussed. Consider a frame attached with the inclined plane, and this frame will be our non-inertial frame because speed of the box is asked with respect to plane. So it is obvious to use here the work energy theorem in non-inertial reference frame. So we are drawing redrawing the figure somewhat enlarged. We show the box in initial and final position. Say here initially, V initial is 0 because box starts sliding from rest on the inclined plane, and after some time when it descends height h, let us assume its velocity V final is V, and this is height h, is descends height h. So how much distance it has traveled? What is displacement of the box with respect to the inclined plane? That is from here to here, and you can see that will be h cosec theta. So that is displacement of the box, h cosec theta. Now we have shown initial and final position. Now we are in a position to calculate initial and final kinetic energies. And by drawing free body diagram at some intermediate state, say here, and showing all the forces acting on the body, real as well as pseudo, we can easily calculate work done by all the forces. So let us show the FBD. So here the box is shown at some intermediate stage. So forces acting on it are its weight mg, and that will make an angle theta with the normal to the inclined plane and normal reaction. Again, pseudo force ma naught, as we have discussed, pseudo force is product of mass of the body and reverse acceleration of the non-inertial frame. So acceleration of the frame is towards left, so pseudo force will be towards right, and its value will be a naught. Now what we do, we resolve the forces into their components along the displacement h cosec theta and perpendicular to the displacement. So let us resolve mg and ma naught both. For the purpose, we'll do some geometrical construction. We construct a triangle here. See this one. This line will be equal to mg sine theta, and this line will be equal to mg cos theta. So let us show them. Mg sine theta. This is component of mg parallel to the displacement vector, and this is mg cos theta, component of mg perpendicular to the displacement vector. Similarly, we construct a triangle here this way. So this will be equal to component of ma naught perpendicular to the displacement vector, and this line will represent component of ma naught parallel to the displacement. So let us see ma naught sine theta, that is component perpendicular to the displacement, and this is what ma naught cos theta, that is parallel to the line of displacement. Of course, we can say anti-parallel. So this component is opposite to displacement, so work done by this force ma naught will be negative. Now we are in a position to write initial and final kinetic energy of the box with respect to inclined plane, as well as with the help of this free body diagram and this displacement to calculate work done by all the forces on the box with respect to the inclined plane. So initial and final kinetic energies. K initial will be 0 because speed is 0, and K final is half mv square because finally we have assumed speed to be v. Now we show work done by various forces, and for this we calculate work done by gravity. So Wg will be mgh. Why it is mgh? Either we calculate product of force magnitude and component of displacement along the force. So displacement, this h, its component along mg is h, so we can see mgh, or we can see in some other way this mg sine theta and this displacement. So it will be again mg sine theta into h cosec theta, again mgh. Now we'll do work done by normal reaction, that will be 0 because normal reaction and displacement are perpendicular to each other. Now we calculate work done by the pseudo force. We denote it by WP, here P for pseudo force, that will be minus ma naught h cot theta. Why? Because this force ma naught cos theta and h cosec theta we multiply, so what we get? Minus ma naught h cot theta. Now we substitute these values in the work energy theorem, and what we get? W initial to final is equal to K final minus K initial, that is formal statement of work energy theorem. For this place what we write? Wg plus Wn plus Wp, and for Kf half mv square, and for Ki 0. Let us substitute the values. Wg plus Wn plus Wp is equal to K final minus K initial. For Wg we have mgh 0 minus ma naught h cot theta is equal to half mv square minus 0. So by solving this we can easily calculate speed of the box with respect to inclined plane when it has slid a distance h cosec theta, or when it has descended a height h. So that speed is v is equal to under root 2h g minus a naught cot theta. Here in this example we have seen use of work energy theorem in a non-inertial frame. For a rectilinear motion we have considered. Now we consider curvilinear motion of a body in a non-inertial frame in the next example. Example 2, work energy theorem in a non-inertial reference frame. A small block is placed on the top of a frictionless dome. The dome is made to move horizontally with a constant acceleration a naught, as shown here. The dome is hemispherical, and on the top this box is placed. If you say small box means size of the box has to be neglected as compared to radius of the dome. Now this dome is made to move here towards left with a constant acceleration. What will happen? Because of inertia, this block will slide towards the right, and its motion will be curvilinear. Of course, if you observe from the ground frame, the path of the box will not be circular, but with respect to the dome, the path of the box will be circular. So again, it will be easy to consider non-inertial frame attached with the spherical dome. But let us see what is asked. A. Find the speed of the block with respect to the dome when it is at an angular position theta while sliding down the dome as shown in the figure. So here, when the box slides from this position to this position at angular position theta, what speed it will acquire, that we have to calculate. So what we do here, again, velocities related to the dome at the initial and final positions and physical as well as pseudo forces at an intermediate stage are shown in the figure. Now we have to show what? Initial velocity and final velocity vector. Let us assume final velocity to be v and initial velocity, of course, it is 0. And again, at some intermediate states, we show all the forces, real as well as pseudo forces. So in the diagram, the dome is shown somewhat larger for the clarity purpose, and on the top the box is here. Its speed is 0 with respect to dome, and at some angular position, say here given theta, let us assume its velocity v final is v, so it is represented here angular position theta. Now the box has slid from here to here. Of course, its path is curvilinear, but displacement is from this position to that position. So let us resolve the displacement into its component along this line and perpendicular to this. So we can show this is what r into 1 minus cos theta, because up to, if you draw this line, that will be equal to r sine theta. So here this is r and theta, and this line will be equal to r cos theta, and this was total r. So from here to here, what is the length? R minus r cos theta. So we can take r common, so it will be r1 minus cos theta. Now we represent the box at some intermediate stage here and show all the forces, real as well as pseudo. So one force is mg and normal reaction, and this acceleration was in this direction, so ma0 will be reversed in this direction. And here we show infinitely small displacement dr vector. Why we are showing it? It will help us to decide the work done by normal, because this dr vector at every instant will be perpendicular normal reaction, so work done by normal will be 0. And for mg and ma0, to calculate their work, we use this displacement component, because these two forces are constant forces. Initial and final kinetic energies. So K initial is 0 and K final is half mv square, and these kinetic energies are with respect to the spherical dome. Work done by various forces on the box. How? Wg is equal to mgr 1 minus cos theta. It is very easy to see, because gravity is constant force, so we multiply magnitude of weight and displace component of displacement parallel to mg, so that is what r1 minus cos theta. So work done by mg will be that is mg r1 minus cos theta. Now we consider work done by normal reaction, that will be 0, we have seen earlier, and work done by pseudo force. Again, it is a constant force, so we multiply the force magnitude and component of net displacement along the force, that is r sine theta. So work done by this pseudo force is ma0 r sine theta. Now we substitute these values in the expression for work-area theorem, and what we obtain here, W initial to final is equal to K final minus K initial, formal statement of work-area theorem. And for W initial to final, we substitute Wg plus Wn plus Wp is equal to K final minus K initial. Wg is what? Mgr 1 minus cos theta. Substitute these values. Mgr 1 minus cos theta, Wn plus 0, Wp ma0 r sine theta is equal to half mv square for kf minus 0 for ki. Now by solving this equation, we can find the speed of the box at this angle theta. So that will be under root 2r g 1 minus cos theta plus a0 sine theta. And you can verify how we can obtain this result. And this was again not very difficult. And we have demonstrated how we can apply work-area theorem in a non-inertial frame, particularly in circular motion. Now, a very interesting question arises. Whether this block will keep on sliding on the box till the ground, or it will leave the box or dome at some intermediate stage. So in the next part we discuss this idea. Find the angular position and at which the block leaves the dome. That what we have seen. We have to find that angular position at which the block will leave the dome. So what we do here, for the purpose we have to use Newton's law. Here it is very important. We have discussed in the last lecture also that where to use working theorem and where to use Newton's laws. Newton's law involve instantaneous quantities, mass into acceleration. Acceleration is instantaneous. Again, force is always instantaneous. So Newton's law can be used only to describe what is happening at an instant or point of time. But working theorem involves change in speed over a space interval. So wherever a body displaces, space interval is given, and we have to relate that space interval with change in speed. We have to use working theorem. So for this purpose, we have to use Newton's law because we have to explore what is happening at the moment when the block is leaving the dome. So we have to explore what happens at the point of time when the block leaves the dome. Thus, we have to make use of Newton's second law. So what we do, where the block leaves the dome, the force of normal reaction vanishes. Conditions at this place are shown here in this diagram. Suppose at this angle phi, the block is leaving the dome. So at this point, normal reaction will become zero. So only forces acting on the block with respect to dome are gravity and pseudo force. So mg, that will be at angle phi with this radius, and ma naught. Now we resolve mg along tangential and normal component because in circular motion we have to consider tangential normal acceleration. But before we resolve, let us show tangential and normal acceleration of the block multiplied by masses as we see kinetic diagram. So normal direction and tangential direction. So that is the block mv square by r. We are assuming at this point speed is v. So that is normal component of effective force and ma tau. Now we have to consider only normal direction because we know because normal reaction is zero. So we resolve this mg, that will be mg cos theta, cos phi because this angle is phi, and this is what mg sin phi. Now we had to resolve ma naught also. So that is again this angle will be phi. So this component will be ma naught cos phi and this will be what ma naught sin phi. Now which component we have to consider? Of course, if we consider ma tau, what we get? Ma tau is equal to this vector plus this vector. So by that equation we can find tangential acceleration. But here we are not interested to find tangential acceleration. In what thing we are interested? Just how this normal reaction is becoming zero. Because in this direction this is this force and opposite this force, and difference of these two forces must be equal to mv square by r. Let us do this idea. So summation fn is equal to man. So what we can write, mg cos phi minus ma naught sin phi is equal to mv square by r. Mg cos phi minus ma naught sin phi is equal to mv square by r. Now what we do? In the previous part we have calculated the speed of the box at some angular position theta. Now taking help of that result, we express v as angular position phi and substitute this value. Substituting the expression for velocity of the block v is equal to 2rg 1 minus cos phi plus a naught sin phi obtained in the previous part, we get, if we substitute this value here and after some manipulation, what we get? Phi is equal to cos inverse 2g upon 3 g square plus a naught square root minus tan inverse a naught by g. So this is the angular position phi at which the block will leave the dome if the dome is accelerating with the constant acceleration a naught. So again you can see the idea was not difficult. Suppose if you had to solve this b part only, again you have to decide two things. What? The condition of leaving the block. That is what is happening at a point of time, normal action is 0, and that we can incorporate only by using Newton's law. And in that, what you need, v mv square, or speed of the block at phi. For this purpose, either you can use tangential acceleration, or more simple version is what, to use work-energy theorem, because to find speed at this position, what we is given, the space interval and change in speed, because initial speed was 0. So the speed we calculate by work-energy theorem, and by using these two expressions we can find this result. Now we proceed further on some other idea, kinetic energy of a system of particles. Because now, as we had discussed earlier, today's lecture will devote the use of work-energy theorem in inertial frame and non-inertial frame. Thereafter, to discuss how to use work-energy theorem for a system of particle. So, for a system particle, how we can write total kinetic energy of a system of particle? Let us see. The kinetic energy K of a system of particle is defined as the sum of kinetic energies of all the particles constituting the system. So that is very simple idea. Consider a system of n particles of masses m1, m2, mi and mn that are moving with velocity vectors v1 vector, v2 vector, vi vector and vn vector respectively. Kinetic energy of this system is given by expression. What we do? We calculate kinetic energies of all the particles. For m1, half m1 v1 square. For m2, half m2 v2 square. For ith particle, half mi vi square. For nth particle, half mn vn square. And we add all these kinetic energies. So total kinetic energy. So K is equal to summation I is equal to 1 to n half mi vi square. So in this way, we can calculate total kinetic energy of a system of particle. Let us see how we can apply this idea by considering a simple example. Example 3. Express the total kinetic energy of the given setup at the instant when velocity of the wave is v. So setup is given here. So we assume the wave to be moving towards here. So when its velocity will be v, we have to calculate kinetic energy of the entire system. So by visual inspection, velocity of the block can easily be decided as shown here. So what if the block is this wedge is moving here with velocity v, the block will be sliding on the wedge with velocity v. At the same time, it will be shifting together with the wedge with velocity v. So here this velocity v and this velocity v. Resultant of these two velocities will show velocity of the block with respect to ground. So now we are not advised to calculate the speed of the box resultant. Only what we do, we calculate the square of speed. So here we can use cosine formula. So K is equal to half capital M V square, that is kinetic energy of the wedge, plus half M V square plus 2v square cos pi minus theta, because we have used cosine rule here in square of that. By solving this, we can write easily K will be half capital M V square plus small m v square 1 minus cos theta. So in this way, we can calculate total kinetic energy of any system. The idea was quite simple as described here. 8 kinetic energy of each and every particle of system. Particle means either it may be point mass or a body in translational motion. Now we explore further what we can do to apply work energy theorem for a system of particles. Work energy theorem for a system of particles. Consider a system of n particles of masses m1, m2, mi, mj and mn respectively. They may be actual particles or rigid bodies in translational motion. As we have seen earlier, the notion particle in mechanics carries two meanings. Either it is a point mass or a body in translation motion. Here a diagram is shown. Several particles, say here m1, m2, mi, mj, m3, mn. All the particles are not shown. Again, as we have seen earlier while describing how to apply Newton's law on system particle, we are using same notation. Here we show capital F1. The capital F1 is net actional force on the M1. Here external force means external for the system. Here similarly capital Fi, net external force on Mi. Small forces F1n, F12, F1i are the internal forces. Here F1i is force on the m1 from the ith particle. F12 means force on m1 from the second particle m2. Force F1n means force on m1 from the nth particle mn. Similarly, we can show the internal forces on mi. That is Fi1 means internal force on mi from m1. Fi2 internal force on mi from m2. Fij internal force on mi from mj. Fin internal force on mi from mn. So let us again describe these notations. Internal forces, of course internal means for system. So these all small letter forces are internal forces. Fij, how defined? Force on ith particle by jth particle. So here on subscript, first subscript denote on which particle the internal force is acting, and second particle, second subscript, which particle is applying that internal force. Similarly, we describe the notation external force. Here external force is the external force for the entire system, and we are denoting that by capital. So capital Fi, how it is defined? Net external force on the ith particle. Here again in this diagram, all the internal forces, all the external forces and all the particles are not shown for the clarity of diagram, or you can say for the better readability of the diagram. Here all the internal and external forces are not shown for the better readability of the diagram. And the same idea we have used while applying, we have learned applying Newton's second law on a system of particles. The work-energy theorem involves initial and final kinetic energy of the system or all the particles. So it is required to denote initial and final velocities of all these particles. So let the initial and the final velocities of these particles be initial velocities. We denote it by u. So u1, u2 and ui and say un. So here u1 is initial velocity for m1, u2 initial velocities for m2 and so on. Similarly, for final velocity we use v. Final velocities v1 vector, v2 vector, vi vector and so on, vn vector. No need to explain, that is v1 is final velocity of m1 and so on. Now we can write kinetic energies and forces also, but we recall the idea what we have done while developing how to use Newton's second law for a system particle. Just recall, we have written an equation of Newton's second law for each particle and then added right hand and left hand members of those equations. The same strategy we'll do here, but instead of writing work-energy theorem for m1, m2, m3 and so on, we can think what will be work-energy theorem for ith particle. Work-energy theorem for mi, that will be work done by all the forces acting on mi, that is work done of this capital Fi and all these internal forces. And this we do what? We write work done by external force separately and work done by all the internal forces separately, and that will be equal to change in kinetic energy of this particle mi. So half mvi square minus half m ui square. So here summation ri vector to rif vector fi dot dr. This term is work done by this external force on mi in carrying this particle from a position vector ri initial to ri final. Now between these two positions we calculate work done by all these internal forces. So how we can write here? Summation j is equal to 1, j is not equal to I, 2j is equal to 1, integral ri initial to ri final fij vector dot dr. So you can see here, this integral is what work done of this force fij, work done of the internal force on mi due to jth particle. Now we sum all such terms varying j is equal to 1 to n, but j cannot be equal to I because to define a force, there must be two bodies. Now these two terms, first term is what? Work done by the external force NMI. Second term is what? Work done by all the internal forces on MI. It is equal to change in kinetic energy of the ith particle. So it will be equal to, say, half mi vi final square minus half mi vi initial square. Now in this way, we can conceive similar equation for all the particles, and by adding their right hand members and left hand members, we can obtain an equation that will be applicable as a work-area theorem for the entire system. Let us see how we proceed with that idea. Referring now the n equations where I is equal to 1 to n, we sum their left hand members and then sum their right hand members to obtain. So let us see. Summation I is equal to 1 to n integral Ri initial to Ri final capital Fi dot dr. So what this term denote? That is, this is work done by external force on Mi, and adding all such term from I is equal to 1 to n means work done by all the external forces on the system. Now we do the sum of the second term on the left hand side. Summation I is equal to 1 to n. Summation j is equal to 1 to j is equal to 1. J is not equal to I. Integral Ri initial to Ri final small Fij dot dri. This is work done by internal forces on what? Mi. And adding all such terms for I is equal to 1 to n, this term will represent work done by all the internal forces on the entire system, and that will be equal to here summation I is equal to 1 to n half mi vi final square minus summation I is equal to 1 to n half mi vi initial square. So this is the entire final kinetic energy system, that is entire initial kinetic energy system. Now if we use such a cumbersome notation, the things will become very difficult. Now let's simplify the notation. The first term on the LHS is the total work done by all the external forces on the system. We denote it by summation W external. So instead of writing this cumbersome expression, we write this simply summation W external. So wherever you write summation W external, what does it mean? Work done by all the external forces on the system. On the same line, the second term on the LHS is the total work done by all the internal forces of the system. We denote it by summation W internal simply. Similarly, the first and the second terms on the RHS are the final and the initial kinetic energies of the system. We denote them by summation Kf and summation Ki respectively. And by using this notation, the work-area theorem will be expressed by very simple notations. The work-area theorem for a system of particles now can be expressed as summation W external plus summation W internal is equal to summation K final minus summation K initial. The first term is work done by all the external forces on the system, and second term here is work done by all the internal forces of the system, that is final kinetic energy of the whole system, that is initial kinetic energy of the whole system. Now total work done by all the external forces and all the internal forces of a system as the system undergoes from one configuration to another is equal to change in kinetic energy of the system between these two configurations. That is formal statement of work-area theorem for a system of particles. This is a formal statement of work-area theorem. Now we pay attention on the second term. Sometimes this term will be 0. Sometimes this term will be equal to decrease in potential energy, or sometimes it will be combination of these two things. So in what case what will happen? We'll discuss later, but today we'll concentrate one thing, that is when this will be 0. Let us try to document all these possibilities what we have I have told to you. That is in a system, total work of all the internal forces will be 0 or equal to decrease in potential energy of the system, or neither of these, or a combination of these. Now Regarding decrease in potential energy or its combination, we'll discuss in later lectures. But today we'll concentrate on the idea when the work done by all the internal forces will be zero. If this term will be zero, the use of work-rate theorem will be greatly simplified. But before we go on this simplification, we try to use work-rate theorem in one example as a process how we have arrived on that result. That is, we apply work-rate theorem on each particle and sum all the right hand member and left hand members. So before we proceed with the further investigations, we first use the theorem to each individual particle and sum the right hand and the left hand members or terms to have a better insight, and then use the theorem for the system as a whole. Now let us see how we can implement all these ideas by taking a simple example. Example 4. The system shown is held motionless. The blocks A and B have masses MA is equal to 10 kg and MB is equal to 20 kg. The inclined planes are frictionless and long enough. The blocks are released simultaneously. Find the speed of A after it slides a distance xa is equal to 6 meter. So that setup is given. So these inclined planes are frictionless and its inclination is 37 degree. Its inclination is 53 degree. And mass of A is 10 kg and mass of B is 20 kg. So what we do? We first apply the work energy theorem on the blocks separately and then sum the right hand left hand members of the equation obtained. So this idea is what we have exactly done, how to write the final statement of work energy theorem for a system. But we use the same process. Instead of applying the final statement, we use the derivation process of that. Constant relation. Actually, to write initial and final contingencies, we must know what is the relation between their velocities. At the same time, if A slides 6 meter, then how much B slides? All these are known as constant relation. So to have this, we can see the initially block A was here, say block B was here, and finally the block A slides this and block B slides this. By visual inspection, we can see how much block B slides, double of that block A slides. So here that assume x, so it will be x by 2. If it will acquire velocity v, it will acquire velocity v by 2. So this constant relation we can write visually very easily. Otherwise, you can use any other method what we had discussed earlier. By visual inspection or any other suitable method, we can write delta xb is equal to half of delta xa. That is the displacement of block B will be half of displacement block A. It means if delta xa is equal to x, so what will we have? Delta xb will be 6 by 2, that is 3 meter. Now what VB is equal to half of VA, that we have seen here. So if VA is equal to V, then VB is equal to V by 2. So we have written initial and final speeds and the relation between their displacement. Now we can write initial and final contingencies, and by drawing free diagram at some intermediate stage, we can write expression for work done of all the forces on each particle separately. Initial and final kinetic energies of the bodies. So Ka initial is equal to 0 because it was at rest, and Ka final is equal to half mb square, and m is 10 and v is we are denoting v, so it was 5v square. So that is initial kinetic energy of A and that is final kinetic energy of A. Similarly, we can write initial and final kinetic energies of the block B. So Kb initial is 0 because it starts from rest, and Kb final is equal to half, and mass of the block is 20 kg and v by 2 is speed, we assume v by 2, so it will be simply 2.5 v square. So we have written here initial and final kinetic energies. Now we calculate work done by all the forces. Work done by all the forces on A. So we draw its free body diagram. So block A is here. Tension T is acting. You can see here. It's mg 100 Newton, and it will be at angle 37 from the surface normal. and here will be normal action. There is no friction. So we have shown all the forces. Now we show the displacement of the block A and resolve these forces into their components along displacement and perpendicular displacement. Let us resolve the force mg. So this will be 60 Newton and this will be 80 Newton. Now we show the displacement of the block. So this is what this displacement block A is 6 meter. Now by this diagram we can write work done by all the forces on block A. So WAG means work done by gravity on A. So 60 into this 6, so they are in opposite, so it will be what? Minus 360 joule. WAN work done by normal on block A will be 0 because displacement and normal are perpendicular. W by tension on A, that is 6 into T, because T and 6 meter, so their product will be 60 joule. Now we can write total work done by all the forces on the block A. So that is summation WA is equal to minus 360 plus 60 joule. On the same manner, we can write work done by all the forces on the block B. So work done by all the forces on the block B, we draw FBT of the block B, that is here tension T and tension T, its weight 20 Newton, it will make angle 53 degree from surface normal. So we resolve this 200 Newton into its component and show the normal action also. So that is normal action NB, and component of 200 Newton along the displacement and perpendicular displacement are this. So that will be 160 Newton and this is 120 Newton. Now from here we can write NB is equal to 120 Newton. And now we show the displacement, that is 3 meter downward. And with this diagram we can write force work done by all the forces. So W by gravity on B 480 joule, 160 into 3, that is 480 joule. W by normal will be 0 because normal is perpendicular to this displacement, and W by tension will be negative 2T into 3 with minus, so again minus 60. So W by tension on B is minus 60 joule. Now we can write total work done by all the forces on B, that is WB summation is equal to 480 minus 60 joule. Now we can substitute these values in work-area theorem separately on these two blocks. Substituting these expressions in the work-area theorem, we get for the block A, W initial to final is equal to K final minus K initial, that is formal statement of work-area theorem for a single particle. So for block A, it will be summation WA, that is equal to Ka final minus K initial. Now substitute the values here, this value. So what we get, minus 360 plus 60 is equal to 5A square. Same thing we do for block B. So block B, formal statement of work-area theorem, W initial to final is equal to K final minus K initial. So here summation WB is equal to KB final minus K initial. For this we substitute this value. So 480 minus 60 joule is equal to 2.5 V square. Now what we do? We add the right hand left hand members. Adding the right hand and left hand members of these above two equations, we get, if we add this left hand side and right hand side, what we get? 120 is equal to 7.5 V square, because this 6 plus 60 and minus 60 will cancel out. And by solving this, we get V is equal to 4 meter per second square. Now we can see one thing here. The tension was the only internal force between the two blocks and its work is being cancelled. So if we can predict priorly that work done by tension will cancel, so we can save some amount of time, and that is what simplification, what I was mentioning earlier, what will happen if work done by all the internal forces will be 0. But now, knowing this fact that work done by internal force is 0, if we apply the work-area theorem on the entire system, what we'll do, let us see. If total work done by all the internal forces is 0, if total work done by all the internal forces is 0, the work energy theorem reduces to the following expression. What? Summation W external is equal to summation K final minus K initial. Here second term is 0. So that is a very simple expression. Now at present, what I am saying, if we know in advance that work done by internal force will be 0, we can use work energy theorem on a system as a whole instead of using it on individual particle. Of course, using the work area theorem on individual particle is basic method. We can use that in any problem. But whenever we get this idea, total work done by all the internal forces 0, we have some simplification. In such cases, it is not necessary to apply the theorem to each body separately, as I am demonstrating for the previous example. So, alternate method of the previous example. Knowing that the total work of all the internal forces is 0, what we can see, we show initial and final position of these blocks, that is final position. So this slides x equal to 6 meter, so it will slide x by 2 is equal to 3 meter. Suppose its velocity is v, its velocity will be v by 2. Now we have to consider only external forces work done. So this T and this 100 Newton and normal, I am showing all the forces. So we are now resolve this 100 Newton into the component 60 Newton and 80 Newton. Similarly, we show all the forces on block B, that is this two tensions and this weight and normal reaction, that is this component 160 and this component 120 Newton. Now we know that work done by all the internal forces 0. So we have to consider only external forces on the system of these two blocks. The external forces are gravity and the normal reactions, and we know the work done by normal reactions are 0. So we will consider work done by gravity only. So here what we do, initial and final kinetic energies we can write here very easily. So initial kinetic energy 0 plus 0. So summation K initial is KIA initial plus KB initial, that is 0. And summation K final is it KA final plus KB final. KA final is half m, means 10 kg square. And what is K final? Summation half m 20 into V by 2 square. So that is half into 10 into V square plus half into 20 into V by 2 square, and that will be equal to, say here, 7.5 V square. That is total final kinetic energy. This is total initial energy. Total work done by all the external forces on the system. So how we can write here? W external summation is equal to W external on A plus W external on B. So W external on A is simply, that is minus 360, and that is W external on B is what? 160 into 3, that is 480. So it will be 120 joule. Now we substitute this value in this theorem. Substituting the above values in the work energy theorem of the system, we get 120, or you can first write the theorem. Summation W external is equal to summation K final minus summation K initial. For this we write 120 joule, and for this 7.5 A square, for this 0. So 120 is equal to 7.5 A square. By solving this, we can find velocity V is equal to 4 meter per second square. Here I have told you that knowing in advance, suppose you know that is total work done by all the internal forces 0, we have this simplification. But if you don't know in advance and we have some idea to predict when internal forces total work done by 0, we can have this simplification. So let us decide now the conditions under which total work done by all the internal forces will be 0. When total work done by all the internal forces is 0, and I told you, now we are deciding the conditions under which this total work done by all the internal forces will be 0. If the total work done by all the internal forces is 0, we find a great simplification or simplicity by applying the work energy theorem on the entire system as a whole. Now we discuss some of the most common conditions under which the total work of all the internal forces will be 0. Now I am not writing all the conditions, but some of the most common conditions. And first one is very obvious. First, if there are no internal forces, that is all the particles of the system do not interact with each other. It means if there is no internal force, and obviously in that condition work done by all the internal forces will be 0. And what is second condition? That you have to pay some attention. All the internal forces are due to such interconnecting links that are inertialess and either non-deformable, or if deformable, they are extremely flexible. Now, let us see. Inertialess, in previous problem, interconnected link was a string that was inertialess, means massless. We have assumed it. Of course, it was deformable. A string is deformable, but it is extremely flexible. And again, if they are non-deformable, suppose the bodies are connected by rods which are massless. They are non-deformable, massless. In that condition also, what the internal force the rod will apply, total work done of that internal force will be zero. So what we can see? Here we can summarize by examples. Most common situation fulfilling the above conditions involve interconnections through ideal strings, massless rods, or direct contacts. So instead of applying these two conditions, you can remember these three situations. It means where the blocks or the bodies are interconnected by ideal strings or massless rods, or they are in direct contact. In such conditions, work done by internal forces will be zero. Here I had to make one very important thing. If there is direct contact, there must not be any friction. So the direct contact must be frictionless. So later on, we try to understand these conditions in detail, but at present we consider these three situations: ideal strings, massless rods, and frictionless direct contacts. Under this condition, the work energy theorem reduces to summation W external is equal to summation K final minus K initial. Now we see the question next. What is there? If there is any one of these three or their combination, what we assume? The internal force total work will be zero, and we apply the work energy theorem as a system whole. Example 5. The system shown is held motionless. Masses of the blocks A and B are 4m and m respectively, and the height of the block A is a capital H. The thread and pulleys are ideal. How much maximum height will the box B attain after the system is released? Collision of the block A with the floor is perfectly inelastic. So this system is given. So these blocks A and B are interconnected by a massless strings. So work done by these internal forces will be zero. Now when the block is released, it will move down, and collision of this block A with the floor is inelastic perfectly. So after the collision, the block A will stop there. So during the collision, there is one more force, normal action. It will act as external force. So how we can account work by that normal action? Again, this normal reaction of course will do some work. How we can say? Because just after collision, velocity of this block will lost. So where this kinetic energy goes? This kinetic energy will go or will be consumed by the work done of this normal action, because during collision there are some deformation, and during collision we'll see in the next lecture, next chapter, collision, that during collision normal reactions are taking infinitely large value. When the block B reaches the upper pulley is removed to avoid a collision. So what is there? Of course, suppose the block B moves up to that height. So when the block B reaches here, the pulley is removed just to avoid any collision with the pulley. So what we do here? Constant relation. First we find constant relation, because there is interconnected bodies, and the constant relations are very simple. What? See here. The block A moves a height h, so block B will move height 2h. Just before collision, if the velocity of block A is u by 2, velocity of block B will be u. That is very simple constant. The block B will rise to a height 2h when the block A strikes the floor. In addition, at this point of time, if the block A hits the floor with a velocity or a speed u by 2, the block B has an upward velocity u. Now second, process after A hits the floor. What will happen after that? The block A will stop here, and the block B will keep on moving under gravity, and string will become slack until it stops by gravity. So this way, that is intermediate state, and after some time, say block B stops here, so we finally here. So during this motion from here to here, the string is slack. It means there is no string tension. The block B is moving under gravity only. After the block A hits the floor, it will stop there. The string becomes slack, making tensile force to vanish, and the block B will continue to move upwards under influence of gravity only until it stops. So that is entire process we have explained. Now if we apply the work energy theorem to the interconnected system of the blocks A and B, total work of tensile forces of the string will be zero, because we have seen earlier the external force, gravity, will work during downward motion of block A and upward motion of block B, and normal reaction from the floor during the collision. That is very important idea. Again, during collision, normal reaction will acquire infinite value. Of course, that is unknown. So, how to calculate work done by this unknown force, we don't know. So, what we do, some other idea. We analyze the process in two stages. First stage, up to here, when the system is released, to just before the collision. And second stage, upward motion of block B after collision of the block A from the floor. So let us see how we do it. I am again showing the diagrams, all the situations here. Now we have assumed that after this situation, the block B rises to height small h and stops here. The force of a normal reaction during the collision is unknown. Therefore, we apply the work energy theorem in two stages of motion, that are stage 1, from the initial moment to the moment immediately before the collision, and second stage, from immediately after the collision to the moment when block B stops. So we apply the work energy theorem for the two stages on the entire system as a whole. Initial and final kinetic energies of the system in the first stage of motion. So we can write here K initial of the system is equal to K A initial first stage plus KB initial first stage, that is 0 because both the blocks were at rest, and summation K final of first stage, KA final of first stage and plus KB final of first stage. KA final of first stage half into 4m into u by 2 square, because this velocity is u and this velocity is u. So what we have here, half into 4m into u by 2 square plus half into m into u square, and that will be equal to mu square. You can verify it. Now we write work done by all the external forces during this from here to here. 4 mg is acting downward during distance h, so work done will be 4 mg is positive, and on B, mg is acting downward and displacement is 2h upward, so work done will be minus mg into 2h. So total work done by external forces will be 2 mgh. Let us see how. Total work done by all the external forces on the system in the stage 1, that is summation W external is equal to summation W external on A plus summation W external on B. 4 mgh minus mg into 2h, so that will be 2 mgh. Substituting these values in the work energy theorem, we get velocity u of the block B. Velocity u means here. This velocity u when the block A strikes the floor. So summation W external is equal to summation K final of the first stage minus K initial of the first stage. So here 2 mgh is equal to mu square, and from here u is equal to root 2 gh. So at this stage velocity of the block will be root 2 gh. Now for further analysis, either we can use work energy theorem or we can make use of third equation of the constant acceleration motion and find this small h. For the second stage of motion, either by work energy theorem on B or third equation of constant acceleration motion, we find that B will further rises to a height small h is equal to h. That is very simple, and I suppose that you will verify it. So how much total height the B rises? 2h here and h here, so it will be what? 3h. Thus, B rises to a maximum height 3h above the floor. So that is the final answer. You can see what simplicity we have obtained if we can decide before starting problem that total work done by all the internal forces will be 0. Now we demonstrate the same idea in next example, example 6. In the setup shown, the rod A can move in the vertical direction and wedge B on the horizontal floor or plane. Both have equal masses m each. Assume friction to be absent everywhere and setup released from rest. This is setup, very well-known setup. I have chosen this one because at this juncture of time, I don't want you to involve much in constant relation. So here the constant relation is very simple and we'll see how it is. What the first thing is, find shift in the rod during a horizontal movement x of the wedge towards right. That is simply constant relation. For this constant relation, we can use method of visual inspection. And how it is? Let us the block, and if the wedge moves here, the rod slides here. So this point of wedge was here, so this was delta xb and this is delta xa. Let us show them delta xb, delta xa, and you can say this angle will also be theta, so we can write very easily delta xa is equal to delta xb tan theta. Relation between displacements of the wedge and the rod is delta xa is equal to delta xb tan theta, of course downward. So delta xa is equal to x tan theta because delta xb is given to be x. So this constant relation is very simple to write. Now let us see what is in B part. Find the total work done by normal reaction between the wedge and the rod during a horizontal movement x of the wedge. Now we know earlier that if the bodies are in direct contact and there is no friction, then total work done by the internal force will be 0. Here there is no friction, so the only internal force between the rod and the wedge is the normal action, so its total work done must be 0. But let us demonstrate it. So how we do here? The force of normal reaction from the rod on the wedge and from the wedge on the rod are constant forces, as well as they constitute Newton's third law pair, means they will be equal and opposite. Denoting the normal reaction between the wedge and the rod by n and displacements of the wedge and the rod by delta xb and delta xa respectively. We can show there in diagram work done by the normal reaction on the wedge. Say this is wedge, normal reaction, and say the displacement delta xb. Now this angle will be theta. So the angle between normal reaction and delta xb will be what? 90 minus theta. So because this angle will be 90 and here the angle 90 minus theta. So W and B is equal to n dot delta xb. So n delta xb cos 90 minus theta. So this will be n delta xb sin theta. Similarly, we can find work done by normal reaction on the rod. Work done by the normal reaction on the rod. We draw the free body diagram and only show the normal reaction, and that is delta xa. Angle between n and delta xa is, for this we extend n, so this is angle. What it will be? 180 minus theta. So now we write here WNA is equal to n dot delta xa vector. So n delta xa cos 180 minus theta. So it will be minus n delta xa cos theta. Now we have obtained expression for work done, and we know the constant relation also. What? Delta xa is equal to delta xb tan theta. By using this, we add these two terms and let us see what we obtain. Total work of the normal reaction. So summation Wn is equal to Wna plus Wnb. That is n delta xa cos theta plus n delta xb sin theta. Of course, this term is minus. Substituting the constant relation delta xa is equal to delta xb tan theta, what we get? 0. So summation Wn is 0. Now we have demonstrated here that total work done by normal reaction between two bodies is 0. And why we have seen earlier, when the bodies are in direct contact, if there is no friction, the total work done of the internal forces will be 0. So in this situation, let us see what is C part. That is asked here. Find speed of the rod when the wedge moves a distance x. Actually, this was the part in which we are interested. Here is the area of working theorem, and we know between rod and wedge the only internal force is normal action. Its total work will be 0. So we can apply working theorem on a system as a whole. So what we get? Knowing the fact that the only internal force of the system of the rod and the wedge are the normal reactions between them, and total work done by these internal forces is 0, we can easily apply the work energy theorem on the system as a whole. And constant relation we have obtained earlier. So what the constant relation is? That is delta xp and delta xa, or delta xa is equal to delta xb tan theta. Delta xa is equal to delta xb tan theta. Now delta xa is equal to x tan theta because delta xb is given to be x. So this relation we obtained. Similarly, we can write velocity. So by dividing by delta t, we can find velocity. So VA is equal to VB tan theta. Velocity of B is, if here VB, so VA will be VB tan theta. Initial and final kinetic energies now we can write. The initial and final kinetic energy of the entire system. So for initial, we sum kinetic energy of block, wedge A and rod, that is 0 because both were released from rest. So summation K initial is equal to Ka initial plus Kb initial, that is 0. Summation K final is final kinetic energy of A plus final kinetic energy of B. Final kinetic energy of A is what? Half m VA square plus half m VB square for B. And by using the constant, what we get? Half m VA square, because we have to VA square sec square theta, because we have to find velocity of A, so we substitute velocity of B. So that is the final kinetic energy of the entire system. Work done by all the external forces on the system. Let us see the external forces. External forces are weights of these two bodies, this mg, and normal reaction from the ground and normal reaction from this support, say an S support. Again, you can see work done by this normal reaction will be 0 because displacement rod is perpendicular to NS. Work done by this normal will be 0 because displacement of the wedge is perpendicular to this NF. And work done by this mg will be 0 because displacement of wedge is perpendicular to this mg. So only this mg is doing work. So what is work done? Mg into delta xa. That is work done by all the external forces. So if it is delta xp, that is what? Delta xa, and we know that delta xa is equal to delta xb tan theta or x tan theta. So what is total work done by all the external forces? Mg into this, or that is what? X tan theta. So that is mg x tan theta. So summation W external is mg delta xa, or summation W external is equal to mg x tan theta. So we have obtained total work done by all the external forces, final kinetic energy of the system, initial kinetic energy system, and these values we can substitute in the work energy theorem for the entire system. Substituting these values in the work energy theorem, we get what? Summation W external is equal to summation K final minus summation K initial. So mg x tan theta is equal to half m VA sec square theta. By solving this, we get VA is equal to 2g x tan theta square root into cos theta. So that is, you can verify this simplification. Now we conclude about this lecture and come on homework. Conclusion is that today we have learned how to use work energy theorem in inertial frame, how to use work energy theorem in non-inertial frame, and how we can use work energy theorem on a system of particles. Of course, on a system of particle, in some system we have seen if total work done by all the internal forces will be 0, we can find a simplicity. But if you have any confusion about that total work done of the internal force is 0 or not, what is advised? Consider work energy theorem on each body separately and add the terms of all these equations, you will find the answer. Again, I am revising when internal forces work done will be 0. That is, if the bodies are interconnected and interconnected links are massless and non-deformable, and if they are deformable they must be extremely flexible. As an example, what we can say, if the bodies are connected by ideal strings or massless rods, or they are in direct frictionless contacts, so in these cases work done by internal forces total will be zero, and we can use the simple idea. But again, as a home assignment, what is the first idea? Revise all the ideas and example discussed today in this lecture. That is very important. And again, I'm suggesting homework from the lecture itself. Solve example 5 and 6 by applying the work energy theorem on each body separately, and try to understand the idea when total work done by all the internal forces will be zero. We'll meet in the next term. At that time, we will try to develop idea of potential energy and idea of conservation of mechanical energy. So, thanks for patiently listening. We'll meet in the next class. The words of a language, as they are written or spoken, do not seem to play any role in my mechanism of thought. The physical entities which seem to serve as elements in thought are certain signs and more or less clear images. Albert Einstein.